We will return to our case. So this is the example. So in our case, we have to define W structure. Define W structure on.
So what kind of homology is this one actually?
What is?
The homology of this compactification.
You mean this one?
What kind of homology?
General, as a topological space.
So you forgot the orbital structure?
Yes. Yeah. This is not a Chen-Ran cohomology. Just you take look at it as a topological space. Yeah. And then we want to define W structure on orbital. So in this case, because W has n variables, and then we should have n, capital N line orbifold line boundaries. But for W, we have S monomials, the sum of S monomials. So for each monomial, for example, we write it this way. So for each monomial, we require W. I, L1, Ln, so this is defined as L1, B, I1. Tensor with L, capital N, B, I, N. So this tensor product should isomorphism by some phi I towards the log canonical boundary. So log canonical boundary is the tensor product of canonical boundary with some divisor line boundaries. So here are I from 1 to S. So this is a requirement. And if this condition is satisfied, then L1, Ln, phi 1 to phi S is called the W structure over curve sigma. And we can also define the isomorphism of two W structures. Yeah, I don't know. I don't want to go detail of the definition. You just imagine we have isomorphism, and then we have the definition of modular space. So another definition. Stable W orbicals. Stable W orbicals. So this this is C with some ingredients. So here C is orbital. Orbital with Yeah, with k market points. L, W structure. So n line bundles satisfying the requirements. W structure over genus over C, right? And of course, the underlying, we require the underlying curve, sigma of C. That means we forget the orbifold structure. Just consider the Riemann surface or algebraic curve. So this curve is required to be stable in the usual way. That means the automorphism group is finite. Yeah. So this tuple is called the stable W orbit curves if those conditions are satisfied. Yeah. And then you define this space. This is just the isomorphism class of C.
Is sigma stable or sigma together with the point is stable?
Well, with market points.
Okay.
Yeah. P1, Pk. Yeah. And you take all the isomorphism class together, and then form the modular space called WGK. WGK. So actually this is a stack. We consider the stack of this. Right, this is the Riemann stack. We can prove this. And we also have the stabilization map. From WGK to M by GK. Just forgetting every structures over code.
Actually, so if it's I'm just a general question. So
Yeah.
so if it's the lemma for stack, so your virtual cycle is always in the ordinary homology.
Yes.
So that means you forget about orbifold whatever, which is so why do you ever worry about this orbifold stuff? It's just why do they? I thought that would probably affect your intersection theory, right? So I thought your virtual cycle is used to do intersection theory. So the orbifold structure doesn't affect the intersection theory.
Actually, you can define some.
Maybe they are taking into consideration of the orbifold.
No, yeah, on the orbifold, you can define some equivalent differential forms, local equivalent differential forms, and then you can use those things to define something like Durham cohomology and so on, and then you can prove those things are just is isomorphic to the homology group of. When it taken as a topological space, so this can be proved, yeah. So we can prove. So this is actually a theorem. This stack is a Delimenfeld stack. And this map is finite proper and finite proper and quasi-finite map. Can be proved this one. So finite proper and quasi-finite. Actually, in geometry, you just think as stabilization map as a covering, branched covering map. And the degree, you can, so the degree is, so actually you can compute the degree, St. So this is just G 2G minus 1. Yes, this one. So except this principal component, we can consider modular space related to a graph, to a combinatorial type. So this is the same for the definition of the modular space with the fixed combinatorial type. For example, we have this one. So this can be taken as a substack of this one, right? So gamma here is actually is a graph. Describe the combinatorial type. Of elements, For example, we can consider components. This node curve, right? So this node curve corresponds to the graph, like this way. So the vertex corresponds to the component, and the tail corresponds to the marked points, and this edge corresponds to the node points here. Right. So in this way you get this is a graph. Yeah. So we can use this graph to describe the stratum of this.
So this is a boundary component.
This is boundary component. Yes. It's boundary component. So in the same way, we can define WGK. We can define this. And this is actually a branched covering of M bar gamma. So this is also a branched covering. But the difference is the degree of this map is different to the degree of net one. So this is a crucial point of the study when compared to the study for this modular space. So this one is usually is not this one. Yeah.
So what's the difference?
The difference is for the boundary component, the automorphism group is different. Yeah.
It could be the same, right?
Usually it's not the same.
Oh.
Yeah.
Do you have an example? How about this case?
Yeah, of course, you need to consider orbifold action here. Yeah. So just skip. Yeah.
Hello?
So we also have the degree shifting because of the W structure. The W structure require this modular space is not empty if and only if this number is integer. Degree restriction. So gamma arrow here is a tuple of n components. So each element, gamma I, is a generator. So this is an element in the symmetry group GW, and is a generator of the local group at the marked points Pi. Because the orbit for the action only exists near the marked or node points, right? And then you can restrict to the nearby of marked points. So you get a local group. So this local group is generated by element in GW called gamma I. So you take all the generators together to get a vector called the gamma arrow. So here, the modular space here means we can see all the W curves, stable W curves, having the orbifold action given by gamma arrow, by this one. So you fix the orbifold action at those marked points, and then consider all such orbit curves, all such W curves. So you have the modular space. So this modular space is not empty if and only if this degree conditions hold. So this gives you a restriction. And then I will tell you the crucial. Maybe I will finish in 5 minutes. Okay. And then we have the virtual cycle. So usually for this one, for this combinatorial type, this virtual cycle lives in this space. Tensor the product of this middle dimensional homology class. So the virtual cycle. So we give a combinatorial type, for example, in this way. So this is a tail. This is a tail. And so for this combinatorial type, we have W gamma, right? It's modular space.
So what is W gamma?
W gamma is just WGK gamma.
Oh, same thing.
Yeah, the same. WGK gamma. Yeah, with this type. And then, so tau is actually is a tail. Is the tau's tail in this graph. Actually, it describes the tau marked points. So for this tau marked point, we have a element. We have a group element gamma tau. So gamma tau is in GW, and for this element we have this homology class. We have described it before. So this is Lefty simple. Lefty simple in this space. And then we tensor all the middle dimensional homology group. So I have explained the right hand side of this homology group. So this virtual cycle lives in this space. So we have the virtual cycle.
So what's the meaning of this virtual cycle?
Virtual cycle is a homology class.
Yeah, but not any homology class, right? They have meaning, right?
Right. Here I just, the difficult part is constructed the virtual cycle
Oh, sure.
using the Huijun equation.
Yeah, but
Yeah.
here I just want to understand what is the use of this virtual cycle. It's used to do intersection theory?
Right. I will write down. Yeah. So the principal part is principal component is this one. Is this one. And the important thing is the dimension. Dimension. So this is the dimension. And we can prove. So the first thing we have to use Huijun equation. Using Huijun equation define the virtual cycle. So this took 100 pages to do so. And then you prove those virtual cycles should satisfy the dimension axiom and the other axioms. Yeah. And then finally we have this multilinear map. Linear map. This one. So this is from the state space. K copy of the state space to the cohomology class of M bar GK. So alpha here is alpha 1, alpha k. So each alpha is in this space W in H gamma I. So this map is defined as the degree of the group G to the G power and over degree of the stabilization map times the Pangredo of the push down of stabilization of this cycle. Cap alpha I. Right? So this virtual cycle lives in this space. And then cap. So then cap with some cohomology class. Right? So this part vanish. This part vanish. And then
Exactly vanish?
yes. And then we get yeah. And then we get a cycle in this space.
Okay.
And then push down.
Sure.
Yeah, to the modular space of curves.
How they vanish? So they exactly fit?
No, this is a pairing, not vanish. This is you should pair the cohomology cycle with the homology cycle.
Yeah, I understand. So they exactly one-to-one correspond?
Yes.
Alpha?
Yeah.
Okay. So you mean there's K of them in there also?
Yes. Yeah. You take K. That is K copy. Yeah. So this is a map. So our theory is HW So this is a pairing. And with those multilinear maps and with the unit, so this becomes a COHFT, cohomological field theory. Field theory. Okay, so this means those ingredients should satisfy a series of axioms. Yeah.
So this virtual fundamental class is actually taken into consideration of orbital structure already, because you are having this.
Yes, of course.
All these other terms basically taking care of the orbital structure, I suppose. Gamma,
Right. Yeah. You locally you can take as equivalent forms to represent the cohomologic class. Yeah. All the things are locally equivalent, and then integrate to orbifolds.
Right.
Yeah.
You feel like when you integrate, it feel like doing intersection theory with orbital structure, basically.
Yes.
But you're actually integrating form, or integrating the cohomologic class.
Yeah. So actually, I can write down the correlators and the generating functions, but those are standard. So
how do the Huijun's equation is doing what? Why do they need why do they need Huijun's equation again? Its purpose is to make this. It's already a stack. It's pretty good space, right? So why do you need this Huijun's equation to?
Right. So it's better to leave to the next time.
Sure.
Yeah, I will explain how to use the Huijun equation to define the virtual cycle.
Okay.
The important thing is to find the suitable cohomologic class you need.
Mm-hmm.
Yeah.
Okay.
Mm-hmm.
So thanks, Professor Fan, for this very interesting introduction to the quantum singularity, which looks like very beautiful and modern. Right.
Maybe it's too complicated for the students to follow.
Yeah.
Well, anyway, you can ask me this after class.
So let's thank the professor.
Yeah.